Let's now look at another type of motion, and what we're going to be talking about now is not uniform motion because we're going to be looking at motion that has a constant acceleration. Remember, uniform motion had an acceleration of 0. So this was our definition of acceleration that we saw last week. And if we made a plot of velocity versus time, and we look at this equation, we would notice that this is the slope of that graph. So here is an example of uniform or constant acceleration. The slope of this graph is constant. That means the acceleration is constant because acceleration is the slope of the velocity versus time graph. So we're going to be now having another type of motion. It's called uniformly accelerated motion. This is separate from what we talked about before, uniform motion. Uniform motion was 0 acceleration. Now we have uniformly accelerated motion, which means we do have an acceleration. Now it's the velocity versus time graph that's a straight line, not the position versus time graph. And specifically, the definition is that the acceleration is constant. It does not have to be 0. So here's a velocity versus time graph, and based on this velocity versus time graph, I want you to try to draw me an acceleration versus time graph, knowing that the acceleration is the slope of this graph. So press pause and take some time to work through it. As I said, we're going to be calculating slopes. Let's break this into pieces. First, let's calculate the slope of this part. You can do the math. You just pick 2 points on here. I'm going to do it real fast. Let's let one of my points be v equals 4, t equals 4. That would be like v1, t1. And then v0 equals 0, t0 equals 0. Plug all that in. I find the slope here is 1 meter per second. Let's calculate the slope of this piece here. Let's let our v1, t1 be the position. V equals -2, t equals 8, right? That's this point. And then the other one, the v0, t0 will be this point, where it's v equals 4, t equals 4. Plug all of that in. I find that my acceleration on this time interval is -1.5 meters per second squared. Again, I'm just calculating slopes here. Review how to calculate slopes if you don't know. After that, the slope is 0, so my acceleration is just 0. So we can put all that together. I want to show that from 0 to 4 seconds, I have an acceleration of 1. So I just draw a straight 1 there. From t equals 4 to t equals 8 seconds, I have an acceleration of -1.5 meters per second squared, and then I have 0 after that. So let's keep going with this. Let's do what we did for uniform motion, but now talking about constant acceleration or uniformly accelerated motion. Let's rearrange this graph, this equation here. I get something like v final equals v initial plus a times delta t. This equation lets us calculate our final velocity if we know what our initial velocity is and we know our acceleration and how long we're accelerating. In terms of the graph, this a times delta t is like, there's like a delta t. A times delta t is like the area underneath here. So we also find that the area under this graph gives us our change in velocity. It doesn't give us our actual velocity. This a times delta t would be like v final minus v initial, our change in velocity. We can do some other crazy algebra and geometry here. I'm not going to go through all the derivations, but I'm just going to blah, blah, blah. I'm not going to do it. We could, if we wanted to, calculate our displacement for an object that is accelerating based on its initial velocity, how long it's accelerating, how big the acceleration is, and again, how long it's accelerating. So this is another equation that relates our kinematic variables. It relates our displacement to our initial velocity, the time that we're accelerating, and our acceleration. We can mess around with a few more of these equations and eliminate certain variables to get even another equation that relates our kinematic variables. Okay, I'm going to summarize all of these in a second. I just want to show you that you can get this one from a graph if you wanted to. If you care about it, the derivation, look it up. Here I could get this equation just by taking this one and some of the previous ones and swapping out different terms. Let's put it all together. So these are our main equations that we're going to be working with for the next many, many weeks, okay? So these are called our kinematic equations, and these only work when acceleration is constant. Now, let me just point out this equation here. If a equals 0, that would be uniform motion. This whole term goes away and we have our simple uniform motion equation. So whether you want to write down the uniform equation or not, it's fine because this equation will apply even in that case. You just plug in A equals 0. So what we have here are 4 different equations, and you can kind of see that we have 5 basic kinematic variables. We have our displacement, delta x, we have v initial, v final, we have delta t, and we have acceleration. So there's 5 total variables. Each of these equations involves 4 variables. So the way that we're going to go about solving all of our kinematic problems is we're going to look in the problem and see which variables are they telling me. They have to tell you the value of 3 of them. And which variable are they asking me for? That's a 4th. So there's 4 variables you need to have in your equation. And once you've identified those 4 variables, you can pick which one of these equations you're going to use. And once you pick your equation, you're almost done. You plug in all the variables and chug through the math. Okay? So what I recommend, and what your friendly neighborhood Spider-Man recommends, is that you write these equations at the top of every homework page that you do, because it's so nice to have them right in front of you. And when you're doing the homework, you have these equations right there so that you can look through and say, which equation do I want once I've identified my variables? It's very helpful. In addition to working with these equations, which we're going to practice a lot soon, we also want to be able to understand the relationship between the graphs of our kinematic variables, position, velocity, and acceleration. So let's review what is uniform motion. What does a graph look like of a position graph for uniform motion? What does the velocity graph look like? What does an acceleration graph look like? Just a generic one. Try to just guess. Press pause and try to guess. Well, we know that for uniform motion, the position graph has to be a straight line, because we need a constant velocity. Okay, so we get a straight line gives us a constant velocity. That means our velocity graph has to just be a horizontal line, something constant. And if the acceleration is the slope of this, we need to just give this, this slope is just 0, so our acceleration graph is just 0. Let's compare that to the newer thing we introduced, uniformly accelerated motion. In this case, it's easier, I think, to start with your acceleration graph. We have a constant acceleration that is non-zero. And this value, whatever it is the slope of this graph. So we're going to have a straight line that has a constant slope for my velocity graph. The velocity is changing, but at a constant rate because the acceleration is constant. Now the position graph is a little trickier, but what I want here is a graph that has a slope that is becoming more and more positive, a bigger and bigger value. I want a slope that gets bigger and bigger. And this is something that has a slope that gets bigger and bigger. So it's nice to kind of compare these sets of graphs and understand how they're related. We can also just look at what's true for all types of motion. For all types of motion, it's true that we can figure out the displacement by taking the integral of our velocity. That's the calculus relationship. In terms of a graph, it's the area under the velocity graph. For our velocity, we have 2 different relationships. We can either say it's the derivative of a position graph and therefore the slope of the position graph. Or we can also say it's the change in the velocity is the integral of our acceleration, which is the same thing as saying it's the area under the acceleration graph. And finally, for acceleration, we can say that acceleration is the derivative of velocity, which is the same as saying it's the slope of the velocity graph. So this is just a nice summary of the kinematic relationships we've learned so far. And now we're going to start doing more sample problems.